Inside an internal combustion engine, metallic components slide against each other thousands of times per minute. Without intervention, microscopic peaks and volleys on these surfaces catch and tear, converting kinetic energy directly into heat and mechanical wear. We quantify this resistance mathematically. The coefficient of friction, denoted by the Greek letter mu, is calculated by dividing the force required to slide an object over a surface by the weight of that object. Different parts of a vehicle require entirely different states of friction. The tires rely on static friction against the pavement to grip and propel the car. But deep inside the engine block, kinetic sliding friction between moving components will cause immediate destruction. The thermal reality inside the block is severe. While the liquid cooling system keeps cylinders at roughly 85 degrees, the oil environment runs much hotter. As shown on these track gauges, typical operating temperatures range from 90 to 120 degrees, and in racing engines, this can exceed 200 degrees Celsius. To manage this, engine oil performs a dual purpose. It creates a physical barrier to separate mating metal parts, and it acts as a fluid coolant, absorbing thermal energy and carrying it away from the bearing surfaces. We classify this separation by its thickness. High-pressure rotating assemblies require full film lubrication, where pressurized oil keeps the surfaces completely apart. External components, like steering and suspension joints, use boundary lubrication, relying on a semi-solid grease that does not fully separate the parts. To survive kinetic and thermal loads, an engine cannot rely on grease. It requires a highly engineered, continuously flowing liquid boundary. Oil is categorized primarily by its viscosity, which is its resistance to flow. Historically, this was measured in redwood seconds, the exact time it took a fixed quantity of oil to drain through a specific aperture at a preset temperature. This introduces a chemical paradox. As an engine heats up, the oil's viscosity naturally decreases. The hotter it gets, the thinner it becomes, increasing the risk of the fluid film collapsing entirely under pressure. Chemical engineers solve this using multigrade oils. These fluids contain specialized polymers that expand and contract, allowing a single fluid to fulfill two completely different viscosity specifications. This chart details cold cranking viscosity limits. The first number in a multigrade oil, like the 10 in 10W, represents its winter rating. It must remain thin enough at sub-zero temperatures to allow the engine to crank safely. Looking at the 10W row, the absolute viscosity limit is capped at 3,500 centipoise at minus 20 degrees Celsius. Exceeding this means the fluid is too thick to pump, resulting in a dry engine cert. Moving up, we see SAE grades like 20, 30, and 40, alongside their required kinematic limits at a highly elevated 100 degrees Celsius. That high temperature rating is the second number. In a 10W40 oil, the fluid behaves like a thick SAE 40 grade when hot, providing a robust protective film during high-speed, high-temperature operation. The base stock of these oils varies. Mineral oils are pumped from the ground, while synthetics are chemically engineered from the molecule up. Specific engine architectures, particularly diesels and those with turbochargers, require exact classifications to withstand their extreme internal pressures. Multigrade chemistry neutralizes the temperature paradox, but the fluid needs a mechanical architecture designed to force it into the engine's tightest clearances. The most widespread delivery method is the wet sump circuit, named because the lowest section of the engine, the oil pan, acts as the primary fluid reservoir. This schematic traces the exact mechanical path of the fluid. At the bottom, a gear-type oil pump creates mechanical suction, drawing oil upward from the sump. Before reaching the pump gears, the fluid passes through a gauze strainer at the end of the pickup pipe, blocking large foreign bodies that would destroy the pump. Compare standard hardware to motorsport applications. A factory pickup tube is fine for a daily commute, but high G-forces in racing can slosh fluid away. Upgraded units feature reinforced geometry to ensure the pump never sucks air. Returning to the flow path, the pump pushes high-pressure fluid directly into a paper filter, stripping out microscopic metal and carbon particles. The clean oil exits the filter and enters the main oil gallery, a long, central horizontal drilling through the cylinder block, acting as the primary distribution artery. From this central gallery, separate drillings route fluid downwards, forcing it directly into the engine's main bearings to establish full film lubrication at the heaviest load points. The oil is then forced through hollow diagonal drillings inside the rotating crankshaft itself, delivering pressurized fluid to the big end connecting rod bearings. Simultaneously, a long vertical drilling channels oil up to the cylinder head, lubricating the camshaft and valve gear before gravity pulls it back down. This entire network of internal arteries guarantees every moving component is physically isolated by fluid, but only if the system maintains a highly specific internal pressure plateau. For the main gallery and filter, the strict operating threshold is approximately 400 kilopascals, or roughly 60 psi. If the fluid exceeds this 400 kilopascal design limit, the pressure will violently rupture the rubber oil seals, causing catastrophic leaks and total system failure. To prevent this, the engine relies on an internal mechanical safeguard, the pressure relief valve. In its resting state, a metal plunger is pushed against a seat by a coil spring. Because the oil pump is driven by the engine, it spins faster as engine RPM increases. This causes the main gallery pressure to spike, pushing aggressively against the face of the plunger. Once the internal pressure hits exactly 400 kilopascals, the force overcomes the spring tension. This spring compresses, lifting the plunger off its seat and exposing a lateral bypass channel. This bypass channel instantly bleeds the excess high-pressure fluid directly back to the sump. This mechanical loop caps the system pressure at a safe maximum, regardless of pump speed. In motorsports, monitoring this precise threshold is critical. A dedicated oil pressure gauge allows the driver to track the circuit in real time. Any unexpected surge or drop outside the normal range indicates a dangerous fault. The relief valve acts as the physical governor, perfectly balancing the mechanical output of the gear pump against the chemical viscosity of the oil to protect the engine's seals. The dashboard gauge serves as the ultimate indicator of the engine's tribological health, connecting hidden fluid dynamics directly to the driver. When pressure drops below the minimum operating range, the vehicle triggers an immediate alert. A low pressure warning is a notification of active, unmitigated kinetic friction. These failures stem from two primary vectors: a physical blockage in the mechanical circuit, like a clogged pickup strainer, or the complete thermal breakdown of the oil's carefully engineered polymers. Over time, the fluid acts as a garbage collector. It picks up abrasive carbon soot and sheared metal particles that are too microscopic for the paper filter to catch. It is this specific particulate load that turns clean oil into a dirty black sludge. This necessitates a strict service interval, typically every 16,000 kilometers or 10,000 miles. Draining the fluid physically resets both the chemical properties of the oil and the mechanical baseline of the circuit. This reset requires mandatory hardware replacements: a fresh paper oil filter, a new rubber seal, and a replacement sealing washer for the sump plug to ensure the pressurized circuit remains sealed. Re-establishing the fluid level requires adherence to strict physical rules. The vehicle must sit on an entirely level surface, and the engine must remain off for at least 2 minutes, allowing the oil trapped in the upper galleries to drain back into the sump. Precision is critical. Underfilling the sump will starve the pump inlet of fluid. Overfilling it allows the rapidly spinning crankshaft to strike the fluid reservoir, whipping the oil into an aerated foam that the gears cannot pump. The lubrication circuit is never a permanent installation. It is a highly active, slowly degrading system. Keeping an engine alive requires perfect continuous harmony between fluid chemistry and strict mechanical regulation.